just mention that there are notes available on the website for yesterday's talks. And without any further ado, Nick?
Sure. So I had to buy these knives to go to make dinner one night. So if anyone wants them. Okay. So today, this talk going to talk about matrix factorizations and the B model, the algebraic geometry side of the story. So just to recall what we saw last time. So sorry for repeating a little bit, but actually maybe for the purposes of today's talk I should really change these symbols to be del's. That'll be easier. So we had this coefficient coefficient field, coefficient ring, and this algebra, and we were looking at A-infinity structures where we extended this guy that's just over complex numbers to be defined over R, and we saw that this A-infinity structure was uniquely characterized by its grading, equivariance, the fact that the order 0 product was exterior product, and sorry, this is probably getting invisible for you, so I'll move over here. The fact that we could compute the image of the A-infinity structure maps under the HKR map up to order Q squared. So now we're going to consider a certain category of matrix factorizations, like in Lena's talk. So I know we used the notation R, but I'm already using R for the coefficient ring. So now I'm going to use S for the ring in which we're doing our matrix factorizations. and we're going to be looking at matrix factorizations of this function. Which of course looks very similar to this one that we already have. So this guy was called G. So we equip this ring S with a G grading in this group. And the grading is exactly the same as the one you get on Hochschild cohomology of this guy by the HKR theorem. And in particular, since this guy was the image of the A-infinity structure map, W has degree 2 with respect to this grading. Since, recall, this guy lived in the degree 2 part of this. So both R and the variable Zi are equipped with non-trivial gradings. So now we're going to define a graded version of the category of matrix factorizations.
Now, maybe you can say just explicitly what are gradings of Zi in this?
Okay. I think that's in another set of notes. That I should be able to say. So we had -1. Okay? So if you work out what the degree of this monomial is, it's the sum of these degrees. So we would get 2n plus -1 -1. And this guy is equivalent when we quotient by this. To this, which is equal to 2 direct sum 0, which is degree 2. So similarly, for these guys here, you can do the same computation. Okay, so these graded matrix factorizations, objects are free G-graded S modules X. Together with an endomorphism of S modules of degree 1 and whose square is W times the identity. So in particular, the fact that W has degree 2 is crucial for this to make sense. Now, oh, and I guess I should have, morphisms are as before, and you get a category with a G grading, like this.
So more of them don't have to preserve the grading, just grade.
Yeah, the morphisms are the direct sum of each graded piece. So we construct a matrix factorization, which I guess was denoted like this. It had this differential on it, where these lowercase wi are chosen so that the sum of zi times wi is equal to the potential w.
You don't put any restriction, kind of action symmetric.
We will want to, because that will be one of the things we need. Yes, we will. And then using the homological perturbation lemma, we construct an A-infinity quasi-isomorphism between the endomorphism algebra of this special object and a minimal A-infinity algebra. So the difference from yesterday is that yesterday we were looking at, the ring we looked at had C instead of R here, but you can do everything with this ring R as the base, coefficient ring instead. Everything works out. So we get this.
Remind notations. What is it in the bracket? This is a ring.
Yes.
And what is M squared?
M2, M3, these are the, yes, these are the operations on our,
It's not a maximum again.
no.
That's it.
Yeah, maybe I should have,
No, no, fine.
I should have written mu, that would be less confusing.
Yeah, very good.
So, and this one was exterior product. So just the usual algebra structure on this guy with these del I anti-commute. And we had this lemma that well, maybe we wrote it in terms of the HKR map. Could essentially be phrased as saying that under the HKR map applied to these operations of degree greater than or equal to 3, we ended up with the original potential W sitting inside the Hochschild cohomology of this algebra. Does that sound... So what this...
Sorry, let me try to understand. This algebra is commutative, always on the right side.
Yes, super commutative, yes. So what this meant was something like you take, if you input these generators del 1 through del n in this order into our A infinity product that you cook up from the homological perturbation lemma, the output is sort of the corresponding coefficient of W. So you take that derivative of W and evaluate it at 0. And the proof of this was by summing over trees, and you just see that these are the only terms that contribute to the tree that has a whole bunch of you find out that all the trees vanish except the ones that look like this, and they contribute exactly this guy. Okay. So what this means...
How do you see that other trees vanish?
I'm not saying it's obvious. I'm just saying...
I just want that
yeah.
status. Not okay.
No. But, yeah, I mean, this is a useful piece of sort of intuition to keep in mind, that when you have this matrix factorization corresponding to the skyscraper sheaf at the origin, and you work out its A infinity minimal model, then somehow the higher A infinity products correspond exactly to terms in the superpotential. Right, so, you know, this term So this term here means you have something like an A infinity product that looks like this.
So the lemma is true for any W.
As long as W has degree greater than or equal to 3.
Okay.
It's, yeah. If it has degree 2, then you get some deformations to the product, and you would get maybe some kind of Clifford algebra. So as a corollary, this DG algebra B, which is the endomorphism algebra of this specific matrix factorization we've chosen, so in particular, this guy satisfies all of the conditions that went into our proposition from yesterday. It's G-graded because we have this G-graded matrix factorization category. If you make all of your choices in the construction sim-n equivariant, you can make the A infinity structure sim-n equivariant, which I guess I haven't quite done here. I've kind of chosen an order for them, but you can symmetrize everything. The product is the exterior product, and when we apply the HKR map to the higher order terms, we get this function W plus higher order NQ. So in particular,
Do you get higher orders?
no. No, you don't. Yeah. But that just because that was part of the hypothesis. So as a corollary, by the theorem from yesterday, there exists an automorphism of our coefficient ring and an A infinity quasi-isomorphism between the endomorphism algebra of our Lagrangian L in this Orbifold-Fukaya category and the endomorphism algebra of this special matrix factorization B. So now we have our hands on some mirror symmetry. We have something in the Fukaya category, and it's A infinity quasi-isomorphic to something in the algebraic geometry side, the matrix factorizations. So now we're in business. So the first thing we can do sorry, I'll move over here again. Is we had this this branched cover of xn over Cpn minus 2. So this guy was the complement of the divisor in Cpn minus 2. And this induced a morphism between these two grading data, these abelian groups that grade our categories. And we saw that when you know this orbifold Fukaya category, the branched cover is the pullback of that guy under this induced morphism of abelian groups that grade the categories. So this A tilde is living inside this category that we're really interested in. So to be a bit more honest, I should really say we don't just take A, we kind of take all shifts of A, so that we don't just get one lift of our Lagrangian, we get all possible lifts of the Lagrangian. So that's all this underline means. And then we also have this doing the corresponding thing on the other side. We pull back our category of graded matrix factorizations along this morphism of abelian groups, which remember just means keeping certain graded pieces of the morphism spaces. So how can we understand? So here, this one is living in what we want. How can we see how this guy is related to the equivariant category of coherent sheaves that we're interested in? Well, oh, and maybe, so this one, let me tell you what this abelian group looks like. This one actually splits off Z as a direct summand. So it admits a canonical map to Z. And as far as we're concerned for this relative Fukaya category, this Z part of the grading is all we really care about in the end. So we're actually going to look at the Z graded category that means everything's just the same, except instead of regarding it as having a grading in this group, you forget this guy and just push the grading down to Z. So I denote that like that. Are there questions, or is this?
Kind of change the category if you push gradient to Z. Gradient is part of it.
No. I mean, you change. Well, in what way do you mean? I mean, you.
You forget some part of the structure.
That's right. Yeah.
About effects.
Yes. You forget some part of the structure, and you only remember the Z grading on the morphism spaces. But all of the morphism spaces are the same as vector spaces, just you've forgotten some of the grading on them. All of the A-infinity structure maps are the same. Okay, and this should have a Q here as well. Yes?
So, I'm not sure I quite remember how this whole that thing worked, but I mean, isn't there like a map? Isn't there supposed to be a map from sort of the G
What are you
upstairs
asking?
to the G downstairs? Or,
Yes.
So how does that map go?
It's, you have your branched cover,
Level of groups.
and this induces
And that's what you call P.
that's P.
And then I mean, these two groups now you wrote them as like a very explicit form. Is it possible to say just how that homomorphism of abelian groups looks?
Sure. So why is this guy isomorphic to what I wrote before? You have the long exact sequence for, no, hang on. Well, I can tell you how the map from this guy to this guy looks, or maybe I should say in this direction. So this Z gets sent to a homology class where you just take a fiber and take a generator of H1 of the Lagrangian Grassmannian in that fiber. So that's where that Z maps to. Then these n factors, they map to, so the ith factor, you take divisor di, you take a little loop around it, and you extend, you choose a section of the Lagrangian Grassmannian in X that extends across this little disk that goes through divisor di once, and you take its restriction to the boundary. And then the reason you get this identification is that if you had your divisors like this, if you have some class in H2 of X, CPN minus 2 in this case. And it hit each divisor some number of times. You could cut out little balls like this. And you would get a bunch of copies of these generators corresponding to this. And inside here, you would get some homology between these loops, which, and if you, so you would get some Lagrangian boundary conditions around these little loops here, and you would take the Maslov index of this complex vector bundle with Lagrangian boundary conditions, and that would give you some class in here. So these guys, you know, it looks like there's a null homology between these classes this guy gives, but if you try to collapse it down, you'll still be left with something going around the fiber, and which is the second, which is 2C1 of the original X.
And I mean, like, now you have also an identification of this guy with that, and then there's a map from Z plus Z n mod 1111 to Z plus Z n mod that other relation.
Yes.
It's just an isomorphism, basically?
No, it's not. So I can write that map down.
Right. That's what I was...
Oh, that's what you. Oh, sorry.
Sorry,
I thought you were asking about this identification.
Well, that's also interesting. So.
Okay. So this map sends looks like this. So you can kind of see why these Ji get multiplied by n, because exactly, they're given by these classes that go once around the divisor. So when we have this branched cover that has branching of degree n around the divisor, the image of a class going around once under this map is a class going around n times. So that's why these guys get multiplied by n. And this has to do with how the Maslov index behaves.
And is that map, so that map is not surjective and it's not...
No, it lands in, it's injective. Yeah. So in fact, so the co-kernel of P will be important for us. It's the covering group of this branched cover, which looks like that. So the question now, so to get from our orbifold Fukaya category here, downstairs, to our relative Fukaya category upstairs, we needed to take the guy we computed and play some game with the grading. And the question is, if we play the same game with the grading on our matrix factorizations, why does this give us coherent sheaves? That's what I want to explain now. Okay. For this,
are you planning to get full kind of this inclusion is all the information you need, or in the
no. What I've identified is some particular objects in this category and some particular objects in this category, and they're A infinity quasi-isomorphic up to changing the coefficient ring.
but your endomorphisms in the relative category would be the same? I mean,
The same
it's
as,
full, the output
yes,
is-
yes. Okay. So for the purposes of understanding how this guy is related to coherent sheaves, I need to introduce a new grading datum. Which is called this. This is the grading datum that controls graded matrix factorizations. And now the lemma is that there's a commutative diagram of grading data. Where I will call these guys
And the vertical, right vertical is embedding in the first component.
on the first component, yes. So this is just a lemma that a certain square of abelian groups commutes. And probably not that enlightening for me to tell you what exactly the maps are here. They all look something like this. So now we had this game with the gradings that we played on these matrix factorizations. So we started with something graded down here. We pulled it back to up here and then pushed it forward to a Z grading. we can also start with something graded down here, push it forward to a grading here, then pull it back. And these categories won't be the same, but they'll have a certain relationship to each other. So if we take something that's graded in this group, we can push forward the grading by G, then pull it back by F. But this guy will keep a grading in the co-kernel of this map here. Which just means you take its original grading and you look at its class modulo the image of P. So a gamma grading is the same thing as a gamma star action. Gamma is the character group. Gamma star is the character group of gamma. And if we look at the gamma star equivariant part, which is the same as the part whose grading has degree 0 in gamma, then this is the same thing. It's isomorphic to pulling the grading of V around that commutative square in the opposite direction. So this is just about, abelian groups. Like it's conceptually a bit strange, but there's really nothing mysterious going on here. So what we've done now is this funny grading thing we did to the gradings of our matrix factorizations. We've turned it into a different game, followed by taking an equivariant part. So how does that help us with our goal of relating this to coherent sheaves? I need So suppose we have a Z-graded ring and some element of it which has pure degree n. For example, you might have a polynomial ring where the grading is just the degree, and you might have some homogeneous polynomial. This allows us to equip our ring S with a grading in this GMF of n. Where we put the part in degree J, in degree 0, direct sum J sitting inside this grading, this abelian group here. And we define the category of graded matrix factorizations of W in S to be the Z-graded category given by taking graded matrix factorizations of W, where the grading is in this funny grading datum here, and pulling back by this morphism to Z to get a Z-graded category. And this category is what we call graded matrix factorizations. And there are...
What is the E of W is just in this.
So we're putting, so W has degree equal to n,
Which I put in first.
which means, no, we put it in the second component.
Okay.
So it ends up having degree 0 plus n, which is identified with 2.
Okay.
So this is a legal,
Yeah.
W lies in the right degree. So there are equivalent, I don't know exactly how the next talk will formulate the definition. Okay, same, cool, okay. All right. So now the theorem is, if we take S to be just a polynomial ring over a field, W to be some polynomial of degree n, and such that the projective hypersurface defined by W is smooth, then this graded matrix factorization category, when you take H naught, is equivalent as a triangulated category to the bounded derived category of coherent sheaves. This is a DG category, and we're taking...
So when you take H naught, you should get the usual category.
Yes, triangulated.
When we take this triangulation.
Sorry?
Okay, the claim is triangulation.
Yes. So,
How is compatible to what we heard yesterday? If you forget about grading, in metric factorization, we've seen singularities, not the whole fiber.
they see the singularities of the fiber of W,
Yes.
which is only at the origin. It's only singular at the origin.
Yeah.
But this is...
Sorry, yes, you would.
Okay. I guess I should wrap up. So we can only apply this theorem to, well, as it's published, to the case where we have some ring, some polynomial ring over a field. So I have this. So I have this guy here that I push the grading forward into this grading datum. So this guy sits inside as a full subcategory this graded equivariant, because we had this gamma star, graded matrix factorizations of W. But we need to work over a field to be able to apply this result. So what we get is we map our ring to formal Laurent series in Q, which is a field. And then we look at this guy We've identified this guy in here with this guy in here. And this one, by applying Orlov's theorem, is equal to gamma star equivariant coherent sheaves on the zero locus of this function w. So now we have some piece of the Fukaya category, it's this A tilde. We've identified it with some piece of this category of coherent sheaves. And what remains to do is to prove that this generates that category, which will be the subject of my next talk, and that this generates this category, which is, I guess, a combination of what Uri was telling us yesterday and what Adam will talk about in the next talk. So I guess I should stop there.